Let us continue building the order. At first glance, this looks much more complicated than the one-line examples from earlier. Look at it as a product model, and the structure becomes much easier to read. Order low-line ID identifies the transaction. User low-line ID connects the order to a customer. Item stores the food. Item low-line count tells us how many item entries are active. The price fields use cents. The Boolean fields records promotion usage. The timestamps represent moment in the order lifecycle. The coordinates describe the driver's location. The final two arrays contain human-readable text. Every field originated from a business requirement. This gave us a good point to compare C and Python. In C, the programmer writes the type explicitly, like this. Python allows a more compact form. The simplicity comes from a different type system. C uses static typing in this context. The compiler has stewed type information before the program executes, and the programmer controls memory representation much more directly. Python uses dynamic typing. The name total low-line cents refers to a Python object, and that object carries information about its own type at runtime. Python therefore moves a large amount of type measurement into the language runtime. This gives Python strong development speed and flexibility. C gives the programmer much more direct control over layout, memory, and machine-level behavior. The difference reflects two engineering priorities rather than a ranking between the languages. Once you understand data representation, programming language choice becomes easier to understand. Different systems optimize for different constraints. Operating systems, device drivers, embedded controller, and performance-sensitive libraries often use C or C++. These languages provide fine control over memory, data layout, and hardware interaction. Enterprise backends and transaction systems commonly use languages such as Java, C++, C#, and Go. Large organizations care about concurrency, maintainability, mature ecosystems, observability, deployment, and long-term reliability. Python appears frequently in machine learning, data analysis, automation, scientific work, and rapid application development. Python's ecosystem makes it very efficient for expressing complex ideas with relatively little code. There is also an interesting architectural detail here. A Python machine learning program may call libraries whose performance in sensitive operations running C, C++, CUDA, or another lower-level implementation. The user experiences Python at the top layers while several technology layers cooperate underneath. Web interfaces bring another ecosystem into picture. JavaScript and TypeScript dominate browser-based interaction. When a user clicks a menu item, changes a quality, opens a modal, or watches a card total update, JavaScript-based technology frequently handles that experiences. Native mobile applications may involve Swift on OS and Kotlin on Android. Cross-platform frameworks add further choices. A real scale platform therefore uses many languages at the same time. The browser or mobile interface has one set of needs. The ordering backend has another set. The recommendation system works under different constraints. The mapping service performs specialized geographic computation. The data platform handles large-scale analytics. This is a key shift in how you should think about programming languages. A language is a tool selected for a particular engineering environment. Once the core ideas of data types, control flow, functions, algorithms, and memory become familiar, moving between languages becomes much easier because many underlying concepts remain recognizable. Syntax changes, engineering concept travels surprisingly well. Now I want to connect this topic back to product thinking. Suppose a product manager says we need a restaurant menu management feature. The sentence sounds simple at the product level, and the engineer begins by decomposing it. The menu item needs a name, that's just the textual data. A price needs exact monetary representation. Integer sense provides one simple model. Availability can use a Boolean field. Inventory can use an integer quantity. Average rating may use a floating point value or another carefully designed numeric representation. A fixed menu category can use an enum or a category ID. Promotion participation can use a Boolean state. Each feature therefore produces data requirements. This gives you a much stronger learning method than memorizing isolated keywords. starts with the product, ask what information enters the system, then identify the operations performed on the information. After that, consider range, position, memory, and business meaning. The appropriate type usually becomes much clearer. Before we finish, let us look at one small piece of C syntax. Int total low license equals 2867 semicolon. The semicolon marks the end of the statement. You can think of it as a grammar boundary for the compiler. Programming languages use punctuation to create structure. Parentheses group expressions and function parameters. Braces create blocks. Commas separate elements. Semicolons mark statement boundaries in C. These symbols gradually become visually automatic as you gain experience. The important skill at this stage is reading the meaning behind the syntax. When you see int total low license equal 2867 semicolon, your mental translation can be create an integer variable representing the order total in cents and give it the value 2867. When that translation feels natural, the code starts looking less like symbols and more like a compressed description of the system. This is exactly the cognition shift we want from this course. Let us finish by putting everything back into one mental model. Programming deals with information. The information comes from reality, a person, an order, a payment, a location, a message, a temperature reading, or a business event. Software gives that information a representation. Integers work naturally for counts, IDs, quantities, and integer-based money representations. Floating point types help represent measured and approximate numeric values, such as distance, coordinates, speed, or many scientific quantities. Strings carry human-readable language through character encodings. Boolean values represent logical states and become the foundation of decision-making. Enough to describe a finite set of named states. Structures bring reality values together and create a software model of a real entity. When these ideas combine, a DoorDash order stops looking like on screen in an app. You can start seeing the internal model behind the screen. The restaurant name becomes a string. The bulk quantity becomes an integer. The price becomes cent. The driver's position becomes floating point coordinates. The payment status becomes a Boolean value. The order mode becomes an enum. All of these fields come together inside an order structure. That ability to look through the interface and imagine the underlying data model is an important step toward thinking like a software engineer. So for part 2, we can move deeper into concrete C types: char, short, int, long, float, and double. We can examine the ranges, side and on-site representations, memory size, binary layout, conversations, overflow behavior, and the logic energies used when choosing among them. At that stage, the names of types will already have a context. Instead of memorizing a table, you will asking a more useful question. What information am I representing, and what representation fits that information best? That question will continue to matter far beyond this lecture. It appears in database design APIs, algorithms, distributed systems, machine learning, financial software, and almost every other area of software engineering.